The fifth derivative, n equals 5, I subtract 1 and get 4 factorial. Okay, so I have n minus 1 factorial. Okay, something else.
Negative 1 to the n.
Okay, negative 1 to the n. So be careful here, because when n equals 1, okay, we have negative 1, but when n equals 1, our first derivative is positive. So what do we have to do to change that?
N is plus 1.
Right, n plus 1, good. Okay, so just look out of where the negatives are starting at. So now, when n equals 1, okay, I have negative 1 squared, and that's positive. And when n equals 1, the first derivative is positive. Okay, so now it's correct. Does everyone understand that?
Would n minus 1 be correct too?
Yes, n minus 1 will also be correct. Any other questions? Okay, so now the denominator. Right, just 2 to the n. For example, the fourth derivative is n equals 4, and I have 2 to the fourth, so 2 to the n. Questions? Okay, so now we plug in. Again, if we find the pattern first, then we have to use this top formula, okay, because now we generalized it. We generalized the nth derivative, so we use this top formula. So I have f of x equals the sum from n equals 0 to infinity of the nth derivative of a. A is the center, so a is 2, times x minus 2 to the n over n factorial. Okay? And so now, the last example we just did, all we did was plug in the nth derivative into here. Okay? However, we can't do that this time because our summation should start at 0, but here this pattern only works for n greater or equal to 1. It doesn't work when n equals 0. Okay, so we can't exactly plug it in right away. What we need to do is take the 0 term out and treat it separately. So this summation is equal to the 0 term when n equals 0. So I have the 0 derivative of 2 over 0 factorial times x minus 2 to the 0. And I have plus the sum from n equals 1 to infinity of the nth derivative of 2 over n factorial times x minus 2 to the n. So this right here is an n equals 0 term. Does that make sense? Let's do a side example, okay? If I took the sum from 0 to infinity of 1/2 to the n, okay, I plug in the first few values of n to find the first few terms. So I have 1/2 to the 0 plus 1/2 to the 1 plus 1/2 squared. Okay, this goes on forever. It's an infinite series. So now I could say that that equals 1/2 to the 0 plus the sum from n equals 1 to infinity of 1/2 to the n. Right? Because now the sum from 1/2, the sum from 1 to infinity will just be this part. Right? Okay, and so I can just pull the 0 term out and add it afterward. Okay, or to the side, outside of the summation. Okay, so I can do the same thing here. If I have the sum from 0 to infinity, I could just pull out the 0 term and take the summation starting at 1, and that will be the same thing. Does that make sense? Yes? No? Everyone's okay? Okay. Okay, so now I have the n equals 0 term plus the sum from 1 to infinity. So now what I'm going to do is plug in the 0 derivative of 2, okay? And again, the 0 derivative is just a function itself because we're not taking any derivatives. So I'm going to plug natural log of 2 into here. So this right here equals natural log of 2. And since this summation is from 1 to infinity. Now I can plug that pattern into here since it's for n greater or equal to 1. Okay, and so if this equals ln2, I have 0 factorial is just 1. X minus 2 to the 0 is 1. So the first term is natural log 2. Okay, and again, that's the n equals 0 term. And then I have plus the sum from n equals 1 to infinity of the n derivative of 2, which is this, negative 1 to the n plus 1 times n minus 1 factorial over 2 to the n. Okay, and then I have over n factorial and then x minus 2 to the n. Okay, so this right here is the n derivative at 2. Questions? Okay, so now we just simplify. So I have ln2 plus the sum from 1 to infinity. I want to simplify n minus 1 factorial over n factorial. So n factorial is just n times n minus 1 factorial. Okay? And so now I can cancel it out, and that will just be 1 over n. So I have negative 1 to the n plus 1 over 2 to the n times n, okay, times x minus 2 to the n. Okay, so here, this right here, I'll just explain what we did here. Okay, so we can't generalize the n equals 0 term. So we leave this out. And start summation at n equals 1. That won't ever happen. If it's going to be a term unlike the others, it'll be in the beginning. So maybe it'll be the first term, maybe it'll be the first 2 terms, but it should never only be in the middle. Okay? All right, so again, natural log of 2 was unlike the others because it's not the same pattern, so we just had to pull that out, and then we can generalize the rest. But this only works for n greater than equal to 1, so we had to pull this one out when n equals 0. Yes?
Is it always going to be whatever the unnatural, like it's ln of 2 over there, there's always going to be ln of 2 plus the series, like that number plus the series, or is it going to be?
So you're saying if this was unlike the others, and so this, if this equaled, say, I don't know, e to the 5 or something, are you saying would it be e to the 5 plus the rest? Yes, and so the reason for that is because we have this. Okay, when n equals 0 and 0 factorial is just 1, and this is always, if it's raised to 0, it's going to be 1. So it's always that first term. Yes?
So is that step needed? Like, instead of writing out that, can you just plug in like whatever the first couple? I think it's like first 3 terms.
Yes, I'm just showing you here how to get there, but if you can recognize that right away, then that's fine. Okay? Any other questions? Yeah.
Is there any reason that you can't always find the pattern first and then plug it?
Fine. Yes. For example, the example that we did for sine x, okay, that one you can't find the pattern first. You have to plug in first.
Right.
Okay, and if you try it, you'll see that you can't find the pattern first. Yeah, so just kind of use your own judgment to trial and error.